So last time we did what is known as the Brayton cycle, which is the one that is the ideal cycle or the ideal modeling, like for the aircraft engine. Remember I did a little figure, and basically we say that what is the general model of an aircraft engine is that at the front you have the compressor, which is going to compress the air now. So by compressing the air, you reduce the velocity of the flow to zero, but the function of the compressor is to do what? To increase the pressure, no? So you increase the pressure, then you go to 2, and here generally will be where you have the ignition of the fuel. So basically that means you have internal energy, U plus PV, no? Which is enthalpy. So you have a bunch of energy, and now you transform all your enthalpy from the turbine is to transform all the enthalpy back into kinetic energy. Okay? So that was the problem. And basically we started doing a problem, but I think we did not finish. So in this problem, we needed to find for this data over here for the compressor ratio of P2 over P1 equal to 10. With initial condition P1 equal to 100, T1 equal to 300, and the volumetric flow rate of 5 cubic meters per second, and T3 equal to 1400, we need to find the efficiency of these Brayton cycles, the back work ratio. What is the back work ratio? Is that you know that the compressor, in order to operate, requires power, okay? And the turbine is the one actually that creates the power. So the back work ratio is basically how much work that this creates go back in order to run the compressor. All right? In real life, it would be like a shaft connecting the turbine to the compressor. Okay? And then I think at the end we need to find the net power. So what would be the net power? The power created by the turbine minus the power consumed by the compressor. Okay? So I think we started to work on this problem. We look at this is the ideal case. You know that between 1 and 2, what is the assumption? Is that you are going to assume that there is no losses, so this means they are asymptotic, no? So you see when you do the S graphic, you have S1 equal to S2, and that the turbine will also be isentropic, will be an ideal turbine, so S3 should be equal to S4, okay? So the efficiency basically is the power generated by the turbine minus the power generated by the compressor. By now we know this would just be H3 minus H4, H2 minus H1 for the compressor, divided by Q in, which basically is the one going between 2 and 3. So it's H3 minus H2. And I think we're working in order to find the values for the enthalpies. So we have to find H1, H2, H3, H4. And it looks like we found H1, H2, H3, no, H1 and H2, that's it. So we need to go now to find H3. So what do we know about H3? We know what is the temperature. So probably that should be enough, I guess. And let's see what we can do. So, all right, so H3, let's keep going. So that should be page 121. Lecture 22. We need to find H3. So what do we know about H3? Remember that the substance we have over here, the ideal substance we're dealing is with air. Okay? Like an engine is air. So what do we know? We know T3 is equal from the figure to 1400. Okay? So T3 equal to 1400. Okay, and because it's air, I think we're dealing with the tables 822, which is the ones that open here. So 822 at 1400. Let's see, what do we have? We have that H is going to be equal to 1515.42. Okay? So it's from table 822. At T equal 1400, we have H3 equal to, again, 1515.42. Okay, and we're gonna need it, so instead of going back, we save some time at 1400. Also, we're gonna need the P sub R, which is 450.5. So PR.3 equal 450.5. Okay, so we found H3, now we need to find H4. So what do we know about 4? Okay, so from the figure, it doesn't look like we know too much. So the only thing we will know is that the turbine, the turbine is operating as entropic, so S3 would be equal to S4. Let me see. All right, so we need to know something about to do the problem. So over here, what's happening is this, is that they're assuming, they don't tell us on the problem statement, but basically, once you get from point 1 to point 2, what you're doing is setting the compression to a ratio of 10. Okay? Then what happens is that this will be your control volume here, and within 2 and 3, the pressure ratio remains the same. Okay? So now what's going to happen on the turbine? On the turbine, you're going to go from a pressure ratio over here that would be, whatever, 10 times higher, and it's going to go back to the atmospheric pressure. All right? So what does that mean? So in this case, we have P2 over P1 was equal to 10. That's going to mean that in this case here, P3 over P4 is equal also to 10, no? Yeah, so basically it means that you compress the air, here is compressed, and now you're going to decompress it back to the outside at 4. So the pressure at 1 and 4 should be the same because the heat exchangers will operate at constant pressure. Does that make sense? Basically we have here P2 equal P3, and in this case we'll have P1 equal to P4. So that means if P1 equal P2, it means that P3 over P4 will be also equal to 10. Because the heat exchangers operate at constant pressure. Okay? All right, so now knowing that, I know how to solve the problem. So if you want here, we can say because heat exchangers operate at constant pressure, which means basically P2 equal to P3 and P1 equal to P4. All right, so that what do we know from the problem? That P2 over P1 will be equal to P3 over P4, and we know that this is equal to 10. Okay, so using the isentropic relation, something we did the other day, that the ratio of the pressures, P3 over P4, will be equal to what? To the ratio of the P sub R's. So we know this. So from this equation, we can find that PR sub 4 will be equal to PR sub 3 times P4 over P3. Okay, or if we do the numerical application, this should be equal to what? PR sub 4 will be equal to 450.5 times, this is, if P3 over P4 is 10, P4 over P3 is going to be 110, meaning that PR4 will be equal to 45.05. Okay, so remember we need to find H4. So now that we know PR sub 4, what can we do? We can probably go to the tables and we're probably going to have to interpolate. Okay, so you see these ones can be a lot of work. So if we go here, let's see, so P sub R is 45, so it should be somewhere over here. So you have 45.55, you have 810, and 43, you have about 800. Okay, so we do the interpolation. We have to look at this value over here. So what is a piece of R? Yes, we're gonna have to look at 800. We have 45 point. No, we have to look at 780 and 790. No. Okay. So you want to copy those values to do the interpolation. So write down interpolating from table A22. So table A22. We have to look at, what is the value we have? 45.05. So 780, 790. We have that H sub A, H sub B. So 780 is 800.03. 790 is 810.99. P sub R A in that case will be 51.64. P R sub B. No, 51.54, no, 43.35, sorry. And the one would be 45.55. So basically that's what I have from table A22. Okay, by now you should be able to do it without doing the figure, but let's do the figure very quick. What you need to find, you put it on the y-axis, what you know, you put it on the x-axis. So what do we know? We go from point A to point B. And we're trying to find the value over here for PR4. So what do we have? We have H4. If we start from the bottom, should we go to what? H sub A plus H sub B minus H sub A, PR sub B minus PR sub A, times PR sub 4 minus PR sub A. And if you want to go ahead and do the numerical application, but since I have the solution, maybe we can save some time, but go ahead and check. Here they say that should be equal to 808.5 kilojoules per kilogram. But go ahead and check, okay, if you want. All right, thank you. So basically, remember, we did all this stuff because last time we said that the efficiency equation will be equal to this expression, okay? H3 minus H4 minus H2 minus H1, H3 minus H2. So now we got all the different values for the enthalpy, so we can say substituting into the equation for the efficiency, H3 minus H4 minus H2 minus H1 divided by H3 minus H2. Okay, and remember from this equation we have that so let's see, H4 is 808.5, H3 we found H3 to be 1515.42, H2 579.9, and H1 300.19. So let's see, 15 minus 108, this one will be positive, so we want positive, H2 minus H2. So I'll pause and I'll give you time to do the calculation. So basically it should give you 0.457, which would be approximately 45.7%. So you see the efficiency for this one will be 45.7. All right. So the next thing we need to do in this problem is to find out. So now should be very quick. We have all the data. Out of this work, how much is the back work ratio? Is that how much of the power created by the turbine is used to run the compressor? Okay. So basically, we did the derivation, but the back work ratio is basically the percentage of the power that you need to run the compressor. So how much power you need to run the compressor divided by the amount of power generated by the turbine. So if we look at the figure again, what should be the power used to run the compressor? Should be H2 minus H1, no? Okay, this will be H2 minus H1, and the one of the turbine should be equal to what? H3 minus H4, okay? By considering this as the control volume, as we did the derivation, so H3 minus H4. And again, I'm not going to rewrite, we have the data over here, so this will mean that the back-work ratio is equal to, let me write the values, maybe, would be 579.9 minus 300.19 divided by 1515.42 minus 808.5. And this should give you how much of the whole power generated by the turbine is used to run the compressor.
39.6%.
So 0.396, which is 39.6%. All right? So a lot of the power generated by the turbine goes back to the turbine to make it run, no? All right? Okay, and at the end, what do we need to find? They ask us to find the net power in kilowatts. Okay. So to find the net power, so C. All right, so the net power, what should it be? I mean, power should be equal to the power generated by the turbine minus the power used by the compressor. Okay? And they ask us to find this in kilowatts. So this is a problem. They don't ask us to find this per kilowatts would be good per kilogram. That would be good. So what does that mean? That this is going to be equal to the mass flow. The work of the turbine we say was equal to H3 minus H4, and because of the mass, continuity of mass, and the one of the compressor will be H2 minus H1. So in this problem we have all the different H values, but we don't have the M. So let's see, what do we have in order to find the M? Okay, so in order to find the M, we know that this is a steady state, so that means the mass flow will be the same all over the places, no? Okay, so we know so what do we know at point 1? We know the volumetric flow rate. Okay, so let's see, and we know the temperature and we know the pressure, so let's see how can we use that. So let's say at 1, so we know that the definition of the mass flow will also be equal to AV1, okay, divided by V1 Okay, and here we could use the ideal gas relation, which is what? PV, so P1, V1 will be equal to R T1, meaning that V1 will be equal to what? R T1 divided by P1. So this will mean that M, the volumetric flow rate, will be equal to R will be equal to AV1 divided by R times T1 divided by P1 where what is R? R will be the universal gas constant divided by, I think it's 28.97, let me check. Yeah. This is the molar mass of air. Okay? And R bar is the universal gas constant. That one should be on your tables. But since I have it, I give it to you, it's 8,314. So if we do a numerical application, look like this is going to be AV1 was equal to 5 cubic meters per second. So let's break over the units. 5 cubic meters per second divided by R, which is 8,314 divided by 28.97 times T, that should be in Kelvin. T1 is given to us in Kelvin, which is 300. Okay, from here. And now P is given to us in kilopascals. So let's just move it. Yeah, let's move it to, so it would be divided by 110 to the 3 pascals. And check, but when I look at the solution, that gives 5.807 kilograms per second. So finally, what do we have? The net power is equal to m dot H3 minus H4 minus m dot H2 minus H1, which again, I'm just going to give you, since I have the solution, you can go and check. 2,481 kilowatts. So here guys, one thing, this R power is not 8,314, is 8.314. So this is 8.314 and that gives you the 5.807. All right, and it gives you a net. All right, so one thing, we're gonna redo this problem again very quick, but making the assumption, with making an assumption that personally I would have done from the beginning, okay? And let's see what would be the difference, okay? So, because over here we use the tables, all right, in order to do everything. So, I mean, we're still gonna have to find some values over here, but let's see what we'll have. Okay. So over here I'm gonna write, let us redo the previous problem making the ideal substance assumption that the change of enthalpy is basically proportional to the Cp times the delta T's. Okay, so in that case, what would that mean? So for example, if we had at the beginning of the problem the efficiency, so if we rewrite the efficiency with that assumption, what would we have? We'll have the efficiency should be equal to what? Cp T3 minus T4 minus Cp T2 minus T1 divided by Cp T3 minus T2. So over here you can see right away that you could cancel all the Cp's. And this will give you that this is equal to T3 minus T4 minus T2 minus T1 divided by T3 minus T2. Okay, so from the problem statement, let's see what do we know. We know T1 is 300 Kelvin. We know T3 is 1400 Kelvin. Okay, so let's see. So we are missing basically T2 and T4. All right, so let's see. From where can we find T2 and T4? So let's see at the equations we did. So I'm just trying to find here the correct data. Put these pages over here. All right. All right, so guys, in order to save some time, basically we're going to assume that the variation of the H and the water temperature will be the same, saying that is the same slope. Okay, so I just ask you to divide H2 by H sub A. You tell me it's about 1.07. Is that correct? Okay, so if you do that now, if you multiply that ratio by the T equal 570, you should get T2. Okay, so what is T2? You tell me 574? Okay, so you get like using previous data. If you want, let's write it down. So we did H2 divided by H sub A, which is 579.9 divided by 575.59 And you told me this is approximately equal to 1.07. So I'm doing the assumption now that T2 over T sub A will be also equal to 1.07, and this equal to T2 over T sub A that we say is 570 equal to 1.07, and this was giving us a value of T2 of 574.27. Okay, Kelvin. Okay, similarly, we could probably do the same thing for H4. Let's see what is H4. Where do I have H4 over here? So, what is H4? H4 is right here. So we do similarly for H4. We could do the ratio again of, what is H4? So we can do H4 over H sub A, which is 808.5 divided by 800.03. You will give me what is the ratio, and then you have T4 over 780 equal to whatever that is. And this should give you the value for T4 in Kelvin. That will be 780 something. So I will pause and I'll wait for you to give me the values. So guys, one thing, somebody corrected, this value should be 1.007, which is the same slope, so it's 1.01, okay? And here's also 1.01, the same as this one over here, rounded up to 1.01, so at the end we get these temperatures. So basically at the end, if we go a little bit up in this page, what do we have? Now we can go and substitute into the efficiency equation. Okay, and see what will be kind of the difference on the result. All right, so substituting. Into efficiency equal to T3 minus T4 minus T2 minus T1 divided by T3 minus T2. So what do we get? Let's see, T3 was 1400 minus T4 is 788.25. Minus T2 we found to be equal to 574.27 minus 300. All this stuff divided by 1400 minus 574.27. So does anyone has the value here?
About 0.4087.
0.4087, which is approximately 40.87%. And before, how much we had before? 45.7. Okay? So this one 40.87. If you want, you can do very quick. All right, let's do the other ones. The back work ratio. Before we had that it was equal to 0.5 There we go, backward ratio. Then if we use this expression, should be equal to what? Cp T2 minus T1 divided by Cp T3 minus T4. So it's equal to T2 minus T1, T3 minus T4. So it gives you the backward ratio equal to, so
44.83%.
Okay, 83%. Thank you. And this is compared to the value that we had before of 39.6. We have it right here. So really this should be 0.4483, no? Okay?
Yeah.
All right. And we could do the same thing for the net power. All right? So you see, there's a difference in values. So which one should be more accurate? The one of the temperatures or the one with the H? The one with the H, no? Because there is no the assumption that the Cp is constant. But anyway, you do the assumption, it's not perfect, but basically it's not that off either, no? Okay? It's more or less. So in an exam, if you do one or the other, I don't care about the result, I care about the procedure, no? Okay? So if you explain properly this one, is nothing wrong with this. You understand the material. If you do it the other way, it's also correct, no? All right? So